acid equilibrium and pH. So you remember this? It's the basics. You have an acid, it turns into a proton and a conjugate base. You take the products and you put it over the reactants. Okay, and again, H plus can be written as H3O plus, so we'll use either H3O plus or we can use H plus. And if you use
there's nothing up there, right?
And as you can see, if you have a strong acid, all of the stuff dissociates, right? So whatever you have here turns that into that. So would you expect a large or small Ka for something that dissociates completely? You would expect a very large one. Lots of products, no reactants, because it all went from HA to H and A. So that's what the deal is with strong acids is. Okay, and in that sense, it's not so hard to do a problem with that. As you can see, all of the strong acids completely dissociate from what they were to their conjugate base and H plus, or again, we can call it H3O plus. You can, either word is fine. And it's important for us to memorize the strong acids and bases, okay? Because when you see a problem with one of these chemicals in it, you're going to want to know whether it's one of these that easily breaks up into its components or the less desirable alternative. Okay, so now what if we do not what I refer to as dissociate completely? What if I do not dissociate completely? If I don't dissociate, then I call it a weak acid, and your Ka is going to be small. And the reason is because you're going to have mostly the acid that we started off with, and very few H pluses, and very few A minuses. So that's this graphic representation whereby we have a whole lot of reactant and hardly any products. That's a weak acid. And that's why weak acids don't do much destruction, like vinegar, for example, because there aren't very many of those H pluses to do what acids do, which is ruin things. And you do not need to memorize that, but keep in mind that in this course, for this particular section, we're going to have a specific chart of Ks now that we refer to as Ka for acids. And so whenever we have a problem, you're going to have, let's say, citric acid in the problem, and we're going to know, oh, well, my K is going to be 7.1 times 10 to the negative fourth. So dissociation constants. If the equilibrium lies to the right, the value for Ka lies to the right. You're right. It's going to be large. If it lies to the left, Ka is going to be good. Water, and I mentioned this last time too in the other PowerPoint, is amphoteric. Just the only thing there is, please remember two things. One, the Kw is 1.0 times 10 to the negative 14. That's important to remember. And then two, that water is an acid and a base. So that's, just don't get confused. You're like, wait a minute, I see both acid and base in water. Well, yeah. Okay. And so no matter what happens, in any problem, you know that water at least has this Kw, no matter what. No matter what's in there. Now, obviously, if we have a very strong acid in there, in solution, this will be very small compared to my strong acid and won't matter for much. Just like a piece of your hair weighs something, and you cannot ignore the fact that your hair is made out of matter. However, with respect to your actual weight on the scale, it matters little. If we were to only weigh your hair, that would mean something different than if we were to weigh all of you with your hair. So, water by itself will have this, but it's a very, very small number. Okay? The negative 14, very small number. Even 10 to the negative 12 is much larger than 10 to the negative 14. Okay. Acetic acid and HCN are both weak acids. Acetic acid is stronger than HCN. Let's arrange these bases from weak to strong. Okay, after thinking about it, the answer is, ta-da! Sorry, in this particular program, these subscripts are coming out weird. You can always look at the regular PowerPoint online if that's confusing you. Okay, but all you have to do is think about the opposite. Now, which one did we say is the strongest acid? Which one do we say is the strongest acid? Do you remember all the strong acids yet? HCl is the strongest acid, right? Strong acid. So the Cl part, being the conjugate base, is the opposite. So we call it the weakest. See, you just think of it that way. Okay, in the problem it says acetic acid and HCN are both weak acids. So if they're both weak acids, then what are their bases? Strong bases. Okay, so then you have to put those at the end. Which one is the strongest acid? This one's the strongest. Which one's the weakest acid? And so since HCN is the weakest acid, it's the strongest base. Okay, we'll get used to thinking that way. It'll just take some practice. Let's move forward. So aside from the confusing ways of looking at strong versus weak, like for example a strong acid, HCl. We already know HCl turns into H plus and Cl minus, and they leave off into the sunset. So the fact that this is strong means that this comes apart easily, and therefore Cl's don't really like H's. Okay, Cl's and H's don't love each other. That's the nature of a strong acid. If it was going to be something that was a weak acid, then you know that the part attached to the H really loves H's. So a weak relationship is actually a strong relationship. And I know that's confusing, but just get it into your head that that relationship, the way I just said it, actually exists, right? A strong situation is actually a weak situation, or a weak situation is a strong situation. So just get your mind ready for that type of confusion. Okay, but there's that part, and then there's also the equilibrium problems, which, if you think about it, what did we say pH was as a definition in the last PowerPoint? pH is the negative log of hydronium ions, okay? So, if that's the case, and we have an ice table, what we're looking for is this one. When we find X, we find the concentration of H plus ions, just like we did in the last chapter. But now we do something with that X. We take the negative log. And if we're going to stick acetic acid into a solution, we know that we're going to start with 0 of these initially, and then whatever dissociates from the complex is X. Set up the law of mass action, and you get something that looks like this. And remember, K is given for certain compounds, like this one. K is given, so you can look it up or I'll give it to you. You know that you're going to have 2 parts, X and X. So you're almost always going to have X squared on the top here. Almost always going to have X squared at the top. And you're almost always going to have whatever your starting concentration is on the bottom. But check out this little secret here. A throwback to the last chapter. What happened to my X there? Why? Why? How you know? How do you know? How do you know it's small? Who says it's small? How do you know it's small? What's this magic you speak of? Come on, Yamazaki, Yamachugi. Remember the last chapter? Yamamoto? No. You never talk. You want to make fun of me. Oh. Because of the small k. Remember last chapter we said if k is ultra small, you can assume that x is too small compared to 0.5. It is a value, it's just too small compared to 0.5. So we can't ignore the fact that the value exists, but we can ignore the value compared to 0.5. Just like we can't ignore that piece of hair actually consists of matter. We can't ignore that it exists with respect to your weight. Okay, so hopefully that made sense to you. So once we estimate that x as being insignificant compared to 0.5 and we get rid of it, look how easy it should be to solve this problem. Multiply and then square root. You find this number, and keep in mind, if this is the pH unit, is this my answer? What do I do to fix it? Negative log. Yeah. And so the pH is 2.52. And so the question was, what if I want to find the pOH? Then you would simply do so pOH is quite literally 14 minus 2.52. And now you have your pOH. Conversely, and I have seen people do them differently, you could divide 1.0 times 10 to the negative 14 divided by 3.0 times 10 to the negative 3. You'll get an answer, and then you can negative log that one, and it'll still come out to the same answer. Whatever that answer is. So if you're going to solve a weak acid equilibrium problem, please remember to always list the species, which will be very important. Choose the species that produces the most H pluses. Okay, and this is if there are a bunch of acids in the same container, because we might do that. If one of them is a very strong acid and one of them is a very weak acid, well, a strong acid is going to be the one to contribute the most H pluses. And so for the weak one, we will not care. Equilibrium expression, ice it. Don't forget, the easy way of ignoring the X, there's a 5% rule we're going to check, and that is at the end of the problem, you should be able to check to see that your estimate of ignoring X is okay. Okay, I'll show you how to do that. And then don't forget to always calculate exactly what the problem wants, whether it be, what's this one called? Give me the full thing. What do these little brackets mean? So concentration of ions, or the question could ask for this one, which is a number pH, which is 0 through 14. So consider this solution, HCl. What are the major species? HCl. In solution, what are the major species? H plus, Cl minus, and H2O. Those are all the major ones. Question, what is pH? Wait a minute. Where's my ice table? I just gave you an answer with no ice table? How rude. Why did that happen? Why did I give you pH with no ice table? Going once? Going twice? HCl is a strong acid. Cl dissociates completely. The concentration of HCl is the concentration of H pluses. You dig? Strong acid. The concentration of HCl is the concentration of H pluses because one turns into the other. Next question. What reaction controls pH? When will that equation be the only part that equals pH? Under what circumstance would water be the one that tells you what your pH is? Yes, for a weak acid, right? How low? Really low. Yeah, lower than water. Consider HCN. Ka is 6.02 times 10 to the negative 14, 10 to the negative 10. Kw is 1.0 times 10 to the negative 14. What's the W mean? Water. I didn't call it Ka, I called it the water one. Okay? So we're going to compare this, which is the products over the reactants, compared to this, which is the products over the reactants, the whole entire number, 1.0 times 10 to the negative 10, or negative 14. Which reaction controls the pH? Is it this one or this one? Top or bottom? Top one. It's higher or greater in number than water. Consider 0.8 molar aqueous solution of weak acid. What are the major species? Are H plus and Cn minus the major species? No, not major, because it's weak. It's very weak. So the acid stays mostly as HCN. Did you say H plus? Boo. And again, always remember that there's a whole lot of water in an aqueous solution. Okay? So, give it all you got. Calculate pH of 0.5 molar aqueous solution, weak acid. So try it. So push pause on the video at this time. Ta-da! How far did you get? Yes!